to tell you first about existing coproduct structures, both on symplectic homology and on string topology. And I see Nancy is here. So we'll talk about the Goreski-Hingston coproduct. And then I will tell you about the structure that I define and how I compute it. So please do stop me if you have any questions. Also, if you have something interesting to say, please do stop me. Okay, so let me start by telling you what the settings are. So and I will not be precise, so there won't be many details, and I might screw up some of the signs or the gradings. So so we will work with Liouville domains, and so if you haven't seen it before, what you want to think about are open symplectic manifolds, and so this consists of they have some contact type hypersurface Y, and here at infinity, they look like Y cross R. So they look like a cylinder at R. So Liouville domains, and this is not an exact it's not an exact definitions, but these are open exact symplectic manifolds, which are cylindrical and convex at infinity. And the primary examples being cotangent bundles. So cotangent bundles of smooth manifolds. So we want to try to study the flow theory of such domains. And so we will consider linear Hamiltonians. So they're going to be C2 small here in the interior, and then they're going here in the infinite end, they're going to have some slope tau. So the Hamiltonians we consider are linear at infinity. And we will consider almost complex structure J, which is omega compatible. So I should give this object a name. So this was my symplectic manifold W with symplectic structure omega. So almost complex structure J, which is omega compatible and is also cylindrical at infinity. So to this data, I can consider the so I can consider X sub H. So this is the Hamiltonian vector field. Defined by omega X sub H equals to DH. And so the periodic orbits of such vector fields are going to come into flavors. So we're going to see some constant orbits in the interior, and then there will be some wave orbits of Y in the color. So the symplectic, so the flow theory, the flow complex of these Hamiltonians, so is going to be, so tau here denotes so tau is the slope. The flow complex is generated by one periodic orbit, and the differential counts, as usual, flow cylinders. Okay. So if you have two, so this gives you the Floer homology of H tau J, and if you have two Hamiltonians, which tau one and one, and for which the slope tau 0 is less than tau 1, then you can also define continuation maps, which are also defined by counting some types of cylinders. And this gives you maps from the Floer theory associated to tau 0 to the Floer theory of tau 1. And symplectic homology is cohomology. Sometimes I'll say cohomology and sometimes homology. So sorry about that. This is the co-limit over all tau of okay, so what kind of structure does this admit? So instead of considering cylinders, we can also look at maps from the pair of pens surface. So we can consider a map U. This is not how I should draw it. So we consider U from this pair of pen surface to W, and these maps, we want them to satisfy a parametrized Floer equation. And this defines the pair of pens product. And depending on your convention, this has different degrees. There is one more structure that I want to mention, which is the BV structure. And morally speaking, you want to think about this as the operation that just rotates the one periodic orbits. So maybe you forget that these are parametrized and you can imagine that you rotate them. And this gives you a degree -1 operation. Okay, so what is this gadget? So in general, this symplectic homology is very difficult to compute, but for cotangent bundles, we have Viterbo's isomorphisms, which tells you that the symplectic homology is isomorphic to the homology of the free loop space. So we will talk today a lot about cotangent bundles. So for T star M, and this is not a precise statement, isomorphism gives so it's isomorphic to the singular homology of the free loop space. So the free loop space is just a space of all free loops in M. Well, this was a tautology, but we just look at the space of all loops, and the base point, the starting point of the loops can be anywhere in M. Okay, so now maybe you saw the definition of the product, and you want to try to define some type of coproduct by just looking at the pair of pens upside down. So what about the coproduct? So what you can do is you can try to count you can try to define a similar operation by just looking at maps from the pair of pens where now you have one positive end and two negative ends. But so this type of operation will be, in order to define it, you're going to have to choose some data. So this kind of operations, remember, they're going to be, we're going to count maps into an open symplectic manifold. And in order to ensure that these surfaces don't escape to infinity, you have to impose some conditions on this here on beta and on H. H here is parameterized by sigma. So let me call this sigma. And these conditions imply, so this is first observed by Seidel and then proved by Ritter. So these conditions imply that the naive definition of the coproduct is highly degenerate. And the point is that when you try to define this, these conditions imply that if you have some tau 0 here, tau 1 and tau 2, then these conditions impose that tau 1 plus tau 2 are greater or equal to tau 0, but they don't. But you can, one choice that you can have is tau 2 to be very small. So or tau 1 can be very small. So what does this picture mean? So if the slope of the Hamiltonian is very small in this end, then the only periodic orbits are constant, and so it tells you that this operation for this choice will have in this end will have outputs in constant orbits, and if you look at the other end, it tells you that on the other end of the choices you'll have this degenerate surface, and all of these choices are homotopic. So this tells you that this operation is highly trivial, but it's not completely trivial. So this was first proved for. So maybe I'll say it for cotangent bundles. It's not exactly trivial. So yeah, I'll expand on this in a few minutes again. Okay, so let me just, so I'm going to take a brief detour through string topology and try to tell you why people care about coproducts and what sort of structures exist in those settings. So recall that we had this isomorphism, so between the symplectic homology of cotangent bundles and the homology of the loop space on LM. So on H star of LM, you also have a rich structure. So you can define the Char-Sullivan product. And the idea is if you are in the base loop space and you have two loops, oops, this is not a good picture, but if you're in the base loop space and you have two loops, you can concatenate them and get another loop. But in the free loop space, you can't necessarily concatenate two loops. But the idea is you have an evaluation map from the free loop space to M, which take gamma and evaluates it at gamma of 0. And you can try to take the fiber product over this evaluation map. So what does this mean? If I have two chains of loops, so maybe this is one family of loops, and its image under the evaluation map is going to be this. So maybe I can highlight it. And then I have another family of loops, which its image under the evaluation map is going to be this one right here. And so at this point, I have two loops which share a common starting point, and then I can concatenate. So I can go first around this one and then around that one. So this gives you a way to define a product, which is by Viterbo's isomorphism. So Viterbo's isomorphism gives you an isomorphism also as BV algebras. So this is analogous to the pair of pens product. So just like in symplectic homology, what you can, if you have a loop, maybe let me pause here. Are there any questions? Okay. If you have a loop, you can try to define a coproduct by cutting it at self-intersections. And so you can try to define the trivial coproduct. I mean, this is going to be a highly degenerate coproduct by maybe cutting at t equals to a half. So this is a theorem by Tamanoi, who says that this this coproduct structure is highly trivial. V is highly degenerate. It vanishes in all degrees, degree naught equals to n. And he computes that V of the unit equals to the Euler characteristic times. So A0 here is a class of a point. So in particular, if the Euler characteristic is 0, then this product structure is this coproduct structure is completely trivial, but it's not exactly trivial. So Gorski and Hingston define another coproduct. So with so this is Gorski, Hingston. They define a coproduct by cutting at all self-intersections. So this is going to be now defined by, this is going to now go from the space of loops, but not constant loops. And you take a loop and it has several self-intersections, and at each self-intersection you cut. So this is an operation that is parameterized by I, but again, this operation, it's actually not well defined at the boundary, but it has a boundary, and so you want to mod out by the boundary, and so you only get an operation which is defined on the free loop space mod constant loops. Okay, so you can ask what kind of information these operations know about M, the manifold M. And initially, when Chas and Sullivan defined the Chas-Sullivan product, they were hoping that it will know more than just the homotopy type of the manifold. But then, so this was proved by Cohen, Klein, and Sullivan. And they show that the Chas-Sullivan product is a homotopy invariant. So for a while, people thought that this would be also true for the Gorski-Hingston coproduct, but a recent computation by Floer and Neff shows that this is not the case. So the Gorski-Hingston coproduct is not a homotopy invariant. So this shows you that at least already on the free loop space, we can see that coproduct structures are more interesting than product structures. But Florian actually states precisely what, I mean, he conjectures what this coproduct structure can detect. So let me just, and this has to do with the white torsion. So let me just tell you quickly, I won't define the white torsion, but let me just give you some geometric intuition for what it is via the Escobar-Dism theorem. Any questions? Okay, so if I have a cobordism W and I have inclusions M and M prime that are homotopy equivalences, then, so here I'm assuming that the dimension of W is greater or equal to 6, then you can ask whether W is a product, whether W is diffeomorphic to M cross I. And the content that, so you can associate a so you can associate an element tau in the weighted group, which I'm not defining, but it's a group that you can construct given the fundamental group of M, so the weighted and W is diffeomorphic to M cross I if and only if tau vanishes, tau is 0. And in fact, you can characterize H cobordisms up to isomorphism. So pi 0 of the H cobordism space is exactly given by this weighted group. So so the content of this theorem says that you can classify H cobordisms up to isomorphism by this weighted group. And so given a homotopy equivalence from M to M prime, you can also associate to it tau, F tau in the weighted group, which is 0 if and only if F is a simple homotopy equivalence. So Knapp's conjecture is that the Goreski-Hingston, so if you do F of delta of X, delta here is my notation for the Goreski-Hingston coproduct. So it's not exactly delta of F of X, but there is this correction term, which is X times tau sub F, which there is some trace map which takes, which goes from the weighted group to H1 of LM mod M, and so I'm denoting. So I should have written F tau, but this is the image under this trace map. Okay, so maybe I should mention one more thing about the homology of the loop space. So there is, so this is to tell you that coproduct structures are interesting. There is maybe one more thing. There is the Goreski wall coproduct. So so for the free loop space, we can decompose H star of LM as a direct sum of H star of LM mod M. And this gives you a way to extend. So this gives you an extension of the Goreski-Hingston coproduct to a coproduct which is now defined on all of symplectic homology. Sorry, not symplectic homology, on the entire loop space. So we'll see shortly that there is no such splitting for on symplectic homology, so we cannot have this type of extension. The reason people are interested in this is that the product, and you want a domain where both the product and the coproduct are defined, so you can study the interactions between the two structures. Okay, so let's maybe go back to symplectic homology. So you can define secondary coproducts. And the idea is to just as in the case of the Gorski-Hingston coproduct, your moduli space is now parameterized by the interval, and you interpolate between all the choices that you can make for the slopes of the Hamiltonian. And now this operation has boundary, and so this is defined only on SS plus of W. So this is going to be the high energy part, and this gadget is you just mod out by constant orbit. So as we saw before, these boundary points are going to have outputs in constant orbits. So once you mod out by those orbits, you have a well-defined operation. Okay, so the idea. Okay, so again, the reason. So note that. So maybe okay. So this kind of operation is due to Oensha, Ekholm. I think there was also a version by Abudendalo and Schwartz for cotangent bundles, and then there is some version by Chilibach, Oensha, and Hingston using parameterized weighted one forms. Okay, and so the point is that this operation. So note that the coproduct note the product structure does not descend to an operation on SH plus. So maybe you want to study identities like this. So you take A, B, and then you take the product, and then you do the coproduct, and maybe you want to ask whether this gives you, maybe you can first do the coproduct of A, and then take the product, or maybe you can first do the coproduct of B, and then take the product. But you cannot study these identities because these two operations are not defined in the same domain. So the first theorem in my thesis is that there exists a co-commutative coproduct structure on symplectic homology. So it's now defined in all of symplectic cohomology. It is parameterized by S3. And it's not co-associative. So it has degree 2n minus 3. And it is not co-associative. And the idea is to, again, so you have these family of surfaces, which are degenerate at the endpoints. And what you can do, essentially, morally speaking, is glue the BV operator here at the ends. And now this, so you glue it by letting the asymptotic marker at these ends vary. I should have chosen different colors because this is two different, maybe I should. This is really blue. So the point is that the BV operation kills the constant orbits. And so now you can, so now you have an operation which is parameterized by S1 cross S1 cross I, and you can choose your data so that because the BV kills these boundary terms, you can actually choose your data so that you can collapse the boundary towards S1 cross 0 to the circle at each, and similarly for and similarly at the other boundary, and then you get a operation which is parameterized by S3. Okay, and this operation is not co-associative, so in pictures maybe what it satisfies looks like this. So I'm denoting by different colors the choices of asymptotic markers at the ends of the surface, and what it looks like is like this. So there should be plus minuses here. Okay, I don't know if it's clear what I mean by those colors, but there is some, oops, this is not the right one. But there is this kind of shows you that both the co-Jacobi and the co-associativity fail. Okay, so in light of the degeneracy of the previous coproduct structures, I wanted to compute it, and that was the harder part of my thesis. Is the harder part of my thesis. So to compute it to show that it's not trivial. And the way I do it, so for some time I thought maybe I could have done it using string topology. And recently Natalie Wall told me that it wouldn't have been easier. So I feel a little bit better about that. Okay, so the way to do this is, so this is in the settings of complements of smooth divisors. Okay, so and this is following Diogo and Lissy. Okay, so now the settings are, so we consider an closed symplectic manifold X, and so X omega, and we assume that X is monotone. So omega is integral. And we assume that we have this divisor D, so D monotone, and D is Poincare dual to 2k times omega for k larger than 0. So the idea is to start by, so we have this tubular neighborhood of D, U, and the boundary of U. The boundary of U is some contact manifold Y, and you can choose your contact form alpha, so that choose contact form alpha that is more spot, and such that the rate flow for alpha generates an S1 action. So we have this Y, and we have it fibers over D, and we want the rate flow to flow here in the fiber. So in this case, so the ray orbits they're given by, so parameterized by Y cos Z plus. So each point in Y gives you is a starting point of some wave orbit, and then this integer tells you the multiplicity. Okay, and so the first thing that Diogo and Lisi do is they define the Morse-Bat complex, and the way they do this is we have this xt. We remove u, and we have this now we have this Liouville manifold which we complete. And the kind of Hamiltonians that we choose they're going to be trivial, going to be completely zero in the interior, and then they're going to have some linear slope. So they actually do this for quadratic Hamiltonians, but I mean it works the same for linear Hamiltonians, and in my settings for, I mean I'm going to define the coproduct in these settings, and for that it's better to use linear Hamiltonians. Okay, so what are the orbits? So orbits of the Hamiltonians. So they are given by Morse-Bat manifolds of wave orbits. And then there is also the degenerate. So you also have the constant orbits, which is basically this entire degenerate manifold, degenerate orbits. So you have a manifold of constant orbits, which is given by this W here, given by W. So in this Morse-Bat complex, so this Morse-Bat complex is going to also compute the symplectic homology. Maybe I should have given an example, but let me just first say this first. So the differential, you count some Morse-Bat cascades like this, and where these flow lines are flow lines in Y. So you have to choose some perfect Morse functions also on Y, on D, and you also have some. You might also have some. You also have to choose another Morse function on the interior of W, and you count some flow lines in the interior. And they show that this complex is well defined, even though you have the degenerate orbits. So they show that like the degenerate orbits do not interfere with the definition of this complex. And so I define the coproduct structure in this case, and it looks like you also have cascades. But because, so even though this looks maybe slightly more complicated, but because I'm only considering curves which have one positive input, like all the constructions in Diogo and Lisi extend to show that this separation is well defined. So the second thing that you do is now you had this manifold, and remember that our Hamiltonians were completely zero here, and then they have some slope like this. So the second thing is you stretch stretch the neck, and now you get some manifold which you get two levels. The first one is symplectomorphic to the symplectization of Y, and the second one is your original thing. But the point of stretching in this case is that now, so if we had some curve here, so maybe it looks like this. So then you get, so after you stretch, this is some version of F-T compactness. After you stretch, you get some curve in W plus some curve here in Y cross R. And the point is that now these curves, they are J-homomorphic. And so they're J-homomorphic, and you can, so the idea is to, so these are J-homomorphic, so you can relate them to Gromov-Witten invariance of X. So can relate to Gromov-Witten invariance in X with some tangency conditions in D. So this was my D, and you relate this back to something like that. So if you chose your J correctly, you can take the curves here in the upper level, and these project to the divisor, and the content of, so maybe, let's see. So Diogo-Lisi prove that you can compute the differential in symplectic homology by considering flow lines in W plus these relative Gromov-Witten invariants of XD and Gromov-Witten invariants of D. So I didn't give an example. So the example is the one that I use is, so in this case, so X is the complex projective quadric, and D can be identified with P1 plus P1, and X minus D is symplectomorphic to T star S3. Okay, so I repeat the constructions for, well, not all of the constructions, but what I do is I consider these curves, these cascades after stretching. So now you stretch, and you get these very complicated configurations. Okay, and so the first thing is I proved that so in these settings, the split Morse-Bott coproduct is well defined, and in fact, you only need to consider the simplest configuration. So, so you don't have any complicated, you don't have any buildings, you don't need to consider augmentation planes. You only need to look at curves like this. So again, these are flow lines in Y, and you have this, and this is in R cross Y. And the second thing is, so Lewis in his thesis, he computes the differential for T star S3, and I compute the coproduct for T star S3. So for T star S3, with U, a generator in degree 3, and 1 being the class of the unit. So now I call this coproduct lambda, and we have that lambda of U equals to 1 tensor 1. And so this tells you that, so if you remember the other secondary coproducts, you mud out by constant orbits, but this tells you that this coproduct actually can remember the constant orbits. So you can think about one as generated by, so you have this PSS map from H star of M to SH star T star of M. And you can think about the unit as generated by the fundamental class of M. And this tells you that this coproduct actually knows about the constant orbits, and it remembers information about the filling. Okay, I'll stop here.
Okay, so thank you very much. Any questions for our speaker?
Can I ask a question?
Please.
So what is this coproduct supposed to have some relation to the Fukaya category? Like, is there a coproduct on Hochschild cohomology, or like algebraically defined, or no?
The answer is yes, but it's not, I don't have a precise statement of what it should be. I just know that this coproduct is somehow related to traces, and those traces can be defined on the Fukaya category, so there should be something, but yeah.
Okay, thanks.
So other questions? Well, actually, I had a question. So you mentioned that the coproduct on SH plus kind of is not a homotopy invariant, right? It can distinguish homotopy equivalent manifolds. Would you expect anything like that for this coproduct that you were discussing?
In families, potentially, yeah.
And so this coproduct, can you describe it on, if you restrict to SH plus, can you describe it as just the usual coproduct, and then you compose both outputs with a BV operator, but it also extends to.
Yeah. Yes, exactly. Yeah. So yeah, you can define it like that on string topology, for example, but I don't know how to define it on string topology without appealing to the splitting. But yeah, you can define it on just SH plus if you want to.
I see, but it actually, one of the virtues actually extends to the full SH.
Yeah. Yeah.
I see. So would it be, how hard would it be to take like Neff's examples where you sort of detect Reidemeister torsion and then try to compute your coproduct in those cases? Have you tried to do that computation? Or?
Yeah, that's work in progress. Some of it is work in progress. Yeah. Yeah, that's a good question. I think, I don't know if this coproduct could actually detect the Reidemeister torsion, because it sort of, because the invariants that come from Reidemeister torsion should be, I think, S1 invariant. But it might detect something else. It might detect some action. But this is also a work in progress, so I don't think I can say more about that.
So any other questions for a speaker? Okay, well, if not, thank you very much again for a very nice talk.
Thanks for having me.